All right, today we're jumping into one of the coolest and most fundamental connections in all of physics, the magnetic effects of electric current.
So, let me ask you something. What could a simple copper wire, the kind you have in your house, possibly have in common with the giant molten magnetic engine at the center of our planet? It sounds like a riddle, right? Well, the answer is a hidden force, an invisible field that connects two things we used to think were totally separate: electricity and magnetism. And the craziest part? Our story doesn't start in some fancy, high-tech lab. Nope, it all starts in a classroom, a university lecture, way back in 1820. And it all came down to a complete accident, an accident that would literally change the world.
The person at the center of this was Hans Christian Ørsted. And this one little observation, this tiny detail he noticed, was the very first concrete proof that electricity and magnetism weren't two different things at all. Turns out they were deeply, deeply related.
So, picture this. Ørsted is giving a lecture. He's got a wire hooked up to a battery, and sitting right there on the table is a simple magnetic compass. With the power off, nothing happens. It's just a compass. But the second he flips that switch and the current starts flowing, bam! The compass needle twitches. It deflects. That was the moment. Electricity was doing something. It was creating a magnetic effect.
Now, to really get what Ørsted saw, we first have to wrap our heads around what a magnetic field actually is. I mean, how do you even see a force that's invisible?
Well, a magnetic field is basically the zone around a magnet where its influence, its push or pull, can be felt. You can think of it like an invisible bubble of force that surrounds it.
And we can actually make that invisible field visible. It's pretty cool. If you sprinkle tiny iron filings around a bar magnet, they don't just land randomly. They immediately snap into this beautiful, distinct pattern, tracing out the invisible lines of force. This, right here, is what a magnetic field looks like.
And these lines aren't chaotic at all. They follow a few very strict rules. First, they always flow out of the North Pole and loop all the way back around into the South Pole. They're also always complete, closed loops, no dead ends. See how the lines are bunched up really tight at the poles? That's where the field is strongest. And maybe the most important rule of all, two field lines can never, ever cross each other.
Okay, so that's how a normal magnet works. But let's get back to Ørsted's wire. He stumbled upon electricity's big secret, that it has its own magnetic field.
So what's really fascinating here is what happens when we do that same iron filing experiment, but with a straight wire that has current flowing through it. We don't get that bar magnet pattern. Instead, we get these perfect concentric circles. This is the proof. A current-carrying wire acts just like a magnet, creating its very own unique magnetic field.
That's awesome, but which way are those circles going? Are they spinning clockwise, counterclockwise? Well, luckily for us, there's a wonderfully simple trick for that called the right-hand thumb rule.
You can actually do this right now. Hold up your right hand. Imagine you're grabbing the wire and point your thumb in the same direction the current is flowing. Now look at how your fingers naturally curl around. That's it. The direction your fingers are pointing is the exact direction of the magnetic field. It's really that simple.
Okay, so we've got a magnetic field from a regular magnet, and we know an electric current creates its own magnetic field. So the obvious next question is, what happens when you put them together? What happens when these two fields meet?
Just think about it for a second. Let's say we have the field from a big horseshoe magnet, and we stick a wire with current flowing through it right in the middle of that field. Now we have two magnetic fields interacting in the very same space. What do you think is going to happen?
The result is motion. A force is literally created out of thin air that physically pushes on the wire. The interaction of these two magnetic fields creates a real, tangible force. And get this, this is the fundamental principle behind every single electric motor on Earth. Now, the crucial thing here is that this force isn't random. It's completely predictable. It all depends on two things: the direction of the magnet's field and the direction of the electric current. And here's the cool part. If you reverse the direction of the current, the push on the wire reverses. If you flip the magnet's poles, the push also reverses. It's completely controllable.
So, remember how the right-hand rule helped us find the direction of the field? Well, to find the direction of this new force, we switch hands and use Fleming's left-hand rule. If you make a little finger gun and you point your forefinger in the direction of the magnetic field and your middle finger in the direction of the current, your thumb will automatically point in the direction of the resulting force or motion.
Okay, so we can use electricity and magnets to create motion. That is incredibly powerful. But can we take it a step further? can we use electricity to create a magnet that we can turn on and off?
The key to this is a little thing called a solenoid. Really, it's just a coil of wire wrapped into a cylinder shape. But when you pass an electric current through that coil, something amazing happens. A super strong and incredibly uniform magnetic field is created inside that coil.
And this right here shows you the magic of the solenoid. I mean, if you look at the shape of its magnetic field, it's almost identical to a regular bar magnet. But there is one world-changing difference. The solenoid's field is temporary. It only exists when the current is on. It's a magnet with an on-off switch.
Now, if we take that solenoid and we stick a piece of soft iron inside it, that magnetic field becomes way, way stronger. And with that, we've just built one of the most important inventions in modern history, an electromagnet. So unlike a permanent magnet from your fridge, which is, always on, an electromagnet has just two states. Current on, you have a magnet. Current off, it's just a piece of metal. It's a magnet that you can control.
And that simple idea, a magnet with a switch, unlocks a whole new world. So I'll leave you with this. Now that we know how to build a magnet that we can turn on and off whenever we want, what kind of things can we create with that power?